we will discuss the HFC phase down. Over the next 15 years, we will be experiencing significant changes in the refrigerants that we use every day in the HVAC industry. HFCs, or hydrofluorocarbons, that we use in the trade consist of refrigerants such as R410A, 407C, and R134A. It is important to point out that this is a phase down and not a phase out, meaning that we will see a significant decrease in the HFC refrigerant and equipment production, but not a complete eradication. The purpose of the HFC phase down is to align with global standards set forth by the Kigali Amendment to the Montreal Protocol. Although the United States has not accepted the Kigali Amendment fully, the U.S. government passed the AIMS Act in December of 2020. The AIMS Act gives the EPA authority to approve substitute refrigerants and set the timeline for the phase-down process. The EPA has announced the substitutes for HFC refrigerants will be A2L, otherwise known as low flammability refrigerants. These refrigerants are R32 and R454B when it comes to comfort cooling. The goal of the Kigali Amendment and the AIMS Act is to set a global standard of global warming potential numbers lower than 750, reducing the greenhouse gas effect and either stabilizing or stopping a 5 or a 0.5 degree increase in the Earth's temperature by the year 2050. The following chart depicts the percentages of the phase down through the end of 2036. We will see starting January 1st, 2022, a 10% decrease in the HFC equipment and refrigerant. Starting in 2024, the industry will be required to decrease production of HFC equipment and refrigerant by a total of 40%. The table represented here shows the phase-down steps in order to reach the end goal of an 85% reduction in HFCs. A2L refrigerants will be used as substitutes for the HFC refrigerants. Organizations such as AHRI, ASHRAE, NFPA, OSHA, and the EPA have completed extensive testing on these refrigerants to determine safety and efficiency. Manufacturers such as Daikin, Carrier, and Trane have been building equipment using A2Ls for over a decade in Europe and Asia with a strong track record of safety. As we start to break down A2L refrigerants and their flammability characteristics, we will start with some of the basic definitions. Lower flammability limit, or LFL, is the minimum concentration of a substance in the air that will ignite. Upper flammability limit is the maximum concentration of a substance in the air that will ignite. The minimum ignition energy is the lowest level of electrical spark energy, or millijoules, required to ignite a flame. The burning velocity is the velocity of a flame under stated conditions of a substance concentration in air, temperature, and pressure. This terminology should be somewhat familiar to most of us because of the work we do on natural gas, propane, and fuel oil burner systems during the fall and winter months. As we look at the ASHRAE table, we can see how the different classifications are brought about. If the refrigerant is designated with an A in the first placeholder, it means that it is considered low toxicity. If the refrigerant is designated with a B instead, that would indicate a higher level of toxicity. The number following the first letter indicates flame propagation. This is the ability for a substance to ignite and spread a flame. All refrigerants are tested under the same conditions in order to accurately classify them within this system. A2L refrigerants such as R32 or R454B, when tested at 140 degrees Fahrenheit in atmospheric pressure, have a burning velocity of less than or equal to 10 centimeters per second or 3.9 inches per second. A2 and A3 refrigerants have higher velocities, higher heat of combustion levels, and lower ignition energy levels. As we take a closer look at the testing procedures, Notice that when these substances are tested, they are at a 1% volume at standardized pressures, temperatures, and humidity levels. The 90-degree angle on the top part of the flask is to test the velocity per second of the various refrigerants. When we look closely at the tests, we can notice a flame color variation and how far the flame has spread. And lastly, the table shown here lists, among other things, the refrigerant concentration levels in parts per million, the minimum ignition energy, and the hot surface temperature for ignition in Celsius. 700 degrees Celsius is equal to 1292 degrees Fahrenheit. The two charts shown here are another way to represent the various types of substances and their flame propagation characteristics. The chart on the left shows LFL and minimum ignition energy. Note that the highest probability for ignition occurs on the bottom left-hand corner of this chart, with acetylene being the quickest and easiest substance to ignite. The chart on the right shows burning velocities and heat of combustion comparisons. Note that the substances on the top right of this table burn the hottest and spread the fastest. Substances such as propane, isobutane, and gasoline. One thing to note that is important to understand the differences in the 20 and 100 year GWP numbers. The 20-year column is labeled real due to the fact that many refrigerants break down after 20 years in an open environment. They can be thermally and biologically be changed into a different type of substance. Note that natural refrigerants such as CO2, propane, and isobutane have extremely low GWP numbers in both the 20-year and the 100-year column. This is due to the fact that these refrigerants exist naturally in the environment. Thank you for listening, and as always, feel free to reach out to me with any questions that you may have.